Hello and welcome back, fellow Orgo Warriors. So today we're going to be going over the basics of Enolate chemistry before we actually get into some of the more complex reactions. So let me just put basics here. And this will give you a good understanding and grasp of Enolate chemistry before we actually start doing those complex reactions. So with that being said, what exactly is an enolate? Well, an enolate is basically a derivative of an aldehyde, a ketone, or an ester. And how it occurs is like this. You have your strong base, which will come in, deprotonate the hydrogen. That will then resonate up like that, and that will resonate up like that, giving you a product that looks like, let me do it in purple. I actually never use purple. Looks like this right here. However, the form you're going to use mostly in this section is not this enolate form. You're actually going to want to resonate this back down and resonate this down to actually give you the enolate most reactions are going to utilize, which would then look like this right here. And the same thing could happen with an aldehyde. I'm not going to draw out the mechanism again. And the same thing can also happen with an ester. However, do note the esters do have some specific reaction types that don't utilize this exact, I wouldn't say mechanism, but they just have some unique abilities that we'll actually dive deeper into in some other videos, but not today. So, with that being said, how do you actually form an enolate? Well, like I said, you want to use a strong base and then a protic solvent usually. And then for this form right here, we'll just say the strong base comes in, once again, takes that hydrogen, resonates up, giving you, once again, this product right here, which can then resonate into this product. So that's how you form an enolate. It's pretty simple stuff, not too complex. Now it can get a little tricky with kinetic and thermodynamic products. Now kinetic occurs faster, and thermodynamic is actually a more stable product. Now, depending on the reaction you're using and the reagents you're using, it could prefer either. One that always prefers kinetic is LDA. And I actually have an example of LDA later on in the video, but just do note that LDA prefers the kinetic product. But let's look at an example that actually could form either, and to kind of show you what a kinetic versus thermodynamic product is. So say you react this with NaH. Ignore that. NaH. And we have protic solvent here. So when we react this with NaH in a protic solvent, are we going to deprotonate these hydrogens or these hydrogens? Well, the more stable product, which is your thermodynamic product, would be this enolate form. And the less stable but quicker forming product would be this enolate form. And this is important to note because for some reactions you want the kinetic product, and for some reactions you want the thermodynamic product. So this is your thermo, and this is your kinetic. And when we actually get into some of the reactions, I will explain which one is actually preferred. But for now, just do know that there are two different types of enolates that can form, a kinetic or a thermodynamic. So moving on to some specific enolate reactions. Now, enolates with halogens, what do these do? Well, once again, the first step would be, since we have that strong base, we're going to form our enolate in its reactive form. Didn't mean to do that. Which would look like this. Now then we also have Br2, which looks like this right here. Now this can actually break this bond. This would then become positive, acting as an electrophile, and this would become a nucleophile. And as we know from basic organic chemistry, a nucleophile can attack an electrophile, giving you an overall product that looks like this. Now do note that I only put 1 times OMe and 1 times Br2, because as you see in the next example, we now have excess OMe and we have excess Cl2. So what would this do? Since there's excess, it can continuously deprotonate the hydrogens, opening up the orbital continuously, allowing for as many hydrogens there are to be replaced with the halogens, which would then look like this right here. And that's when there's excess. Once again, the first example only had 1 times and 1 times, but when there is excess of both the nucleophilic base and the halogen, it can replace the hydrogens indefinitely. So, this example, there is something else unique about the halogens. When we react this with a base, of course, and Cl2, we would get this product, since there is excess. Now this right here is what is known as CCl3, and it can actually act as a leaving group. And when reacted with another nucleophile, can be replaced, as shown. Just like that. So those are your halogens, not too hard again. Now moving on to R2CuLi. So R, once again, is just a carbon chain. I should note that. This just means carbon chain. So, such as ET, Me, pH, any carbon chain you can think of is what the R stands for. And how these work is it's going to usually be utilized in a conjugated system. Now, what's a conjugated system mean? This is a conjugated system, meaning that this resonance can occur right here, which would then give you something that looks like this. Positive charge right there. And how this reaction works overall is that resonance occurs, and then the carbon chain at the front would actually act as a nucleophile, come in and attach at that electrophilic position, giving you this product overall. So moving on to pH, CuLi, same thing can happen here. Resonate, resonate, come in, attack. Just like that. Moving on to SN2 reactions with enolates. So we have 1 times of our ketone reacting with NaH. So how that would work is, once again, you're just forming an enolate. And now then we react this with an Br attached to an ethyl. What happens here is Br can act as a leaving group, leaving this orbital open right here. And then this can act as your nucleophile, come in, attack the electrophile, giving you a product that, with the new bond, which I'll draw in red, looks like this. Same thing with this. Once again, prefers the thermodynamic product in this case because, once again, thermodynamic product is more stable. So for the SN2 reactions, you're going to want the thermodynamic product. So your enolate would actually form here, which would then give you this. And then when we react this with Cl attached to an isopropyl, this would leave. This would come in, form a new bond with that, giving you a new bond like that to the isopropyl group, your overall product. So as you can see, these aren't too hard. These are the basics, but it's best to know the basics before you actually start getting into some of the complex reactions. And now then, looking at LDA. As I said, LDA forms the kinetic product. An easy way to think of the kinetic product, if you don't understand stability, is the less sterically hindered position, which is here, because this is more sterically hindered. So it's not going to form here. It's going to form here when it actually deprotonates. So the enolate would actually look like this right here. And then in its resonance form, of course, you could also say the enolate looks like this. And that is how you utilize LDA, prefers the kinetic product. And these are the basics. The next video is actually going to go really in depth on different mechanisms and some different reactions that you're actually going to come across and explain how they occur. But I hope these basics help and you guys have a wonderful day.